Welcome to our webinar presentation. My name is Adam Harris, Managing Director for C-Therm Technologies here. With me is my colleague, Sarah Ackerman. Sarah is the head of our Applications Development Lab. Sarah has been helping us with these webinars. We've done about a dozen of them over the past few months. We're now in a cadence of typically a Thursday afternoon locally for us here, running a webinar on various different topics related to thermal conductivity. We originally started with the focus on thermal conductivity, but we've then also since broadened that out a little bit to bring in some of the expertise from our partners at Metroviv, who's a world leader in dynamic mechanical analysis, and also STA Instrumentation, another elite player in the area of thermal analysis and calorimetry. So we wanted to put together a webinar presentation on the topic of Polymer Characterization 101, basically. The goal of this webinar was to help inform you of the different methods of characterizing polymers and basically help inform, if you were going to set up a lab for polymer characterization, what would you need in that lab to give you a full picture of the performance of that material? Of course, polymers are used broadly, whether it's a recycled polymer or whether you're getting into advanced polymer composites where you're doping them with graphene and other additives. They're in a broad range of applications, from the electronics, the phones we use, the smartphones, TVs, automotive, consumer goods, in a broad range. They're all around us. So we thought this would be an interesting topic for this week, is just looking a little bit at the polymer characterization. And specifically, we're going to be looking at the methods of TGA, DSC, thermal conductivity, STA, and DMA analysis. The webinar should run for approximately 1 hour. I'm going to provide a very basic introduction, and then I'm going to pass this over to Sarah, who's put together a great curated content on this different characterization. So a little bit about C-Therm Technologies. We're based here in Fredericton, New Brunswick, Canada. We're a Canadian organization. We're represented in about 65 countries around the world. Our clients include a broad range of industry and academic researchers, government labs. There's a great list of our testimonials on our webpage, but you'll see groups like NASA represented there, 3M, Honeywell, DuPont, Siemens, and really it's a broad range of applications we support. One of the things personally I love about my job is that the particular niche expertise we've developed, which is in the thermal conductivity characterization, is so beneficial and applicable to a broad range of scenarios. So some days we're working with developers of a baby diaper, a new type of diaper. Other days it's explosives, could be electronics, could be consumer goods, textiles, etc. And that really keeps it interesting from our side. What we are the best in the world at is in innovating and advancing the characterization capability of measuring thermal conductivity. We do that by focusing on the advancement of transient-based methods for thermal conductivity. We'll talk a little bit about how those methods work and the benefits they offer in bringing them to a range of different situations. But we'll really orient today around polymers. This is a lineup of our thermal conductivity and instrumentation products. In the middle, you see Trident. This is a research-grade instrument. It's our most powerful instrument in terms of capabilities and specifications. It addresses a number of industry norms, ASTM and ISO. It has 3 of the most prominent transient methods available for thermal conductivity. The patented MTPS method that we developed, that's the cylindrical shaped sensor there. It's a one-sided interfacial sensor, and it's the simplest and most sensitive method for measuring conductivity. Really easy to get reproducible numbers. If you've got 5 different labs operating around the world, all measuring the same type of sample, the easiest way to get a reproducible result is to use the MTPS method. The needle probe in the middle there, the stainless steel needle. This is our most robust sensor. It's sheathed in stainless steel. It's very robust. It's really designed for polymer melts in very sticky situations where you might be worried about the material bonding to the sensor. So Sarah will highlight its use as part of the response to measuring polymers. Certainly when you get into polymer melts, the needle is a great addition. And then our Flex TPS sensor, the yellowish sensor there to the lower left, this is a nickel foil that's encapsulated in a Kapton material as a dielectric and is typically sandwiched in between two samples. It's called Flex for two reasons. One, the sensor is actually flexible, so it's great for really hard samples like concrete or more rigid materials. It's also about giving more flexibility back to the user. It demands a little bit higher level of training in terms of how to operate the technique. But in return, it gives you a much greater capability in terms of testing anisotropic samples, oriented samples that have a directional dependence in terms of heat transfer. You can test thin films with this method. And of course, you can deal with some bulk materials as well. It's a really great complement to the simplicity that the MTPS one-sided sensor offers. To the left of this, you'll see the TPS kit. This is our most economical offering. It's really oriented towards academic researchers on a very tight budget. It has been picked up a lot in the last few months by researchers locked out of their labs looking to establish some basic capability in perhaps a more remote kind of scenario where they might be working from home or a garage or maybe not have access to their full-scale lab. It does offer a strong basic capability in measuring the conductivity of mostly solid materials, would work on most polymers certainly. Does not meet the ISO standard for TPS. For that, you need the bridge circuit technology that is built into Trident in the middle product picture. On the right of this, you have the TX Touch Experience platform. This is really more oriented towards textiles and consumer goods where you're looking to characterize the touch properties of materials. So whether something feels warm or cool to the touch. Polymers has a lot of application in textiles, and in some applications we very much care what that material feels like. In consumer goods and automotive, for example, you'll get a lot of polymers applied in the interior of vehicles, and they're often painted to look like metal or other objects. They may be used as a replacement for a leather, in some cases on the upholstery. What the material feels like can be very important. If it doesn't feel right, if it feels like plastic, this will often have an impact on the perception of quality of the vehicle. So if it's supposed to look, if it's supposed to look like metal, it should feel somewhat like metal as well. And what the TX Touch Experience platform does is it really quantifies that touch experience from a thermal perspective. So whether it feels warm or cool to the touch. If you'd like more information on this, please enter in the chat box. We'd be happy to follow up with you on it further. It won't be a significant focus of this presentation, which is really on the characterization of polymers. But you'll see Trident heavily featured here. With Trident, it's really about bringing those three most prominent methods for thermal conductivity together in one instrument. And our philosophy here in developing this product a couple of years ago was that it's better to have options in thermal conductivity. There's no silver bullet in characterizing conductivity. That different scenarios call for different solutions. So with Trident, it's one instrument, but three methods for measuring thermal conductivity. This just gives you an illustration of the different sizes of sensors, and this helps inform minimal sample requirements. So you'll see in the top right, the needle probe, the length of the active area is 150 millimeters. This is the area that has to be fully covered by the sample. Again, this will be typically applied for a polymer melt. The middle sensor illustrated is the TPS, and this is available in different size formats. There's a 6, 13, and 30 millimeter diameter sensor available in those different sizes. And there's also different temperature ratings to those sensors that are available, up to 500 degrees Celsius. But that would typically sandwich in between two samples. And then to the left is the MTPS. This is the single-sided sensor. This is the easiest to operate. It has an active area of about 18 millimeters in diameter. That's the area that has to be fully covered by the sample, but it is, as close as you can get to one button push for thermal conductivity characterization. Very much an automated analysis of the sample result. It makes it really easy as a user to do this. We have high school students that come through and operate this equipment with very successful results. So it just speaks to the simplicity of use. I want to just highlight a couple of our partners that we work closely with, both from France. C-Therm, here we're really we're at an elite level when it comes to thermal conductivity characterization. We've really carved out a strong niche for ourselves in this space. The types of groups we tend to want to associate with and build partnerships with are complementary in nature, and also typically operating in that same kind of philosophy of being more at an elite level. So not typically being the low-cost producer in market. Certainly there can be more mass-produced types of instrumentation available, but typically where we operate is more in the specialty area. So really high sensitivity, really high precision. In a lot of cases, higher temperature ranges under more challenging environments, high pressure, and so forth. And STA is a group that we've been working with for over a decade. Their technology is amazing. They developed a 3D calorimeter years ago that is the most sensitive available on the market. They really thrive in providing that kind of experimental control, whether it's temperature or pressure or the sensitivity. The results are top in commercial available instrumentation, and their instrumentation overall is very versatile in coupling with additional analysis, whether that be GCMS or other types of techniques for coupled analysis. So we're very proud of that relationship that we've been developing with them over a decade, and you're going to see a lot of content pulled in from STA in the presentation that Sarah has curated. I also want to make mention of the partnership with Metrovib, another company based out of France, and another company that is at a very elite level when it comes to characterization. So they've developed a very strong reputation in the rubber industry, in tires, and also in polymer composites for the high frequency, high force, and automated platforms that they offer with dynamic mechanical analysis. And you can get a little bit of a sense of their product orientation here. We just did a great webinar with Hugues Bourrier, who's their international sales manager, earlier this week. I think Rosa dropped that into the chat box earlier on. Yes, if you just scroll up, I see it's there. That was a really great webinar, and we've got several other recorded as well. So if you're interested, do check that out. It's a great resource, and you can access it freely at your own convenience. I'm going to jump a little bit ahead. So this webinar is really to provide an orientation. It's designed, although we wanted to provide that little bit of background on the commercial companies involved here, this is an educational webinar, and it is really about helping you understand what needs to be in your lineup in terms of characterizing polymers. Whether or not you go with these exact models or instruments, that's not the point of today's webinar. The point is to really help communicate what are the characterization requirements in dealing with polymers, and why do we measure these particular aspects of their performance. So Sarah's put together a great presentation here. Sarah Ackerman, again, is our lab manager. She heads up the application development group, Thermal Analysis Labs. That's a division of C-Therm Technologies. She's active on a number of ASTM and ISO committees, and is an expert when it comes to this type of characterization. So without further ado, I'm going to stop sharing here and pass this over to Sarah. Sarah, it's all yours. Oh, just check your audio.
Is that better?
Yes, perfect.
Perfect. Sorry about that. There we go. So thanks again for the introduction, Adam. I do appreciate it. You always do a great job on introducing the subject matter and introducing me, so I do appreciate that. Moving into the body of this, this webinar is not focused on complete thermal characterization of polymers, but it is focused on thermal characterization of polymers. So we're not looking at things like chemical analysis, maybe for example, the chemical analysis methods like GCMS or FTIR. Primarily, what we're focused in is the techniques that are looking at the thermal physical properties of polymer materials. And these really fall into three main categories. The first of which is the heat transfer property methods, which primarily are thermal conductivity methods, but also a subset of calorimetric methods. Dynamic mechanical analysis, which measures things like the loss and storage moduluses of the material. And finally, thermal analysis and calorimetry to characterize things like phase changes, thermal stability, and other things like that. So broadly speaking, polymers, if you take a small repeating unit that is a chemical, and it can be anything from something as simple as an ethylene unit to something as complicated as a subunit of some proteins. But if you've got a small repeating unit, that's what we would call a monomer. And if you connect several monomers together with covalent bonds, you can get a short chain polymer, sometimes called an oligomer. And if you extend that long enough, eventually it becomes something that we class under the general category of polymer. So a polymer then is just a macromolecule that is composed of multiples of smaller, simpler chemical units, which are called monomers. So this class of compounds is very broad. Usually they're carbon-based, but occasionally they can be based on other central elements, rather. And they see application in a very wide range of fields, ranging from making the casings of certain types of equipment, to injection molding products, textiles. Some types of polymers are used as gelling agents, or are used. Some polymers are used in the melt phase and are designed to have to be a melt at room temperature. They're increasingly used. Polymer composites are increasingly used in aerospace and aviation applications, like the helicopter blade you see on the lower left there. And as well, you see widespread application of polymers in automotive interiors as well as in tires. So as my previous slide probably made the case for, polymers are ubiquitous in our modern world. I would be hard pressed to find a product in today's day and age that doesn't have a polymer involved in its materials of construction somewhere. Your USB charger probably has at least one, maybe two or three different types of polymer, just as one example. And because they're so widespread, they're a very important technology for our society to continue to work the way it works now. And really making sure that these materials do the jobs we need them to do, and that we understand the characteristics of these materials to enable good process design and good product design is really important in terms of designing processes that will make good performing consistent products. And to design those processes, you need to have a really thorough understanding of their thermal properties. So we can class polymers to start understanding their thermal properties. We kind of want to think about the classification of the polymers that we're dealing with. The general public would usually classify polymers based on the source of the polymer. For example, you can look at natural polymers like DNA, RNA, proteins, rubber, so on and so forth. You can also look at synthetic or semi-synthetic polymers, which are man-made chemicals, sometimes starting from natural building blocks. And generally speaking, the natural polymers will usually have better biodegradability properties. However, increasingly we're getting more tunable synthetic polymers with better biodegradability and better sustainability profiles. A polymers chemist, on the other hand, might look at a polymer and think about classifying them based on their structure. So simple linear polymers versus branch versus cross-linked polymers would be what a polymers chemist might look at and find useful in terms of classifying the material. You might also classify those polymers based in addition to the structure to the chemistry of the material. So what is the repeating unit being used? The final classification, and this is something that some types of engineers would prefer to classify according to, is based on the molecular forces and the molecular properties of the polymer material. So this would be things like elastomer versus thermoplastic versus thermoset versus fiber type of materials. And all of these classifications are oftentimes, you'll see different polymers grouped together differently depending on which type of classification rubric you're looking at. And they all do different jobs for different applications. So moving next into the thermal properties that you might want to measure, the first one we'll look at is mechanical behavior. So mechanical behavior is important for things like, is the piece of the part that we're going to make going to break under routine use? Like if you have a toddler's toy, for example, the level of durability is different than if you have an aerospace part, and in terms of the requirement there. And furthermore, the consequences if a toddler's toy breaks are not quite as serious, although the toddler might disagree with me on that one. But they're not quite as serious as, for example, if an airplane part, maybe in the wing or in a control surface, happens to crack or break down, especially in flight. That would be a disaster. So we want to make sure we understand how these materials behave mechanically, and also what our application is in terms of what do we need as far as the mechanical behavior for the material of construction. So generally speaking, polymers are viscoelastic materials, which means they both tend to deform with force, but when you remove the force, they tend to return to the original shape. So they display both viscous and elastic behaviors. And these properties tend to be very strongly dependent with on temperature. So if you look on the right-hand side, you can see a curve of a common example character looking at characteristics of a polymer, looking at the transition at one from the glassy phase through to the elastic phase into softening and eventual melt. So measuring mechanical behavior of polymers usually looks like DMA method in terms of the best method to measure these properties. So DMA, or dynamic mechanical analysis, is a technique where you measure force and displacement on a polymer as you shake it or apply some sort of deforming force. So if I go back to this side, you'll see the force is going to oscillate periodically, as is the displacement of the specimen. There's two key moduluses that we talk about when we're talking about the mechanical properties of polymers. The first one being the storage modulus, which is roughly defined as how much stress, or so-called internal force, has to be put into the material to cause a certain amount of deformation or strain when you're loading the polymer sample with strain. The storage modulus is kind of analogous to another property that some folks might be aware of called the Young's modulus. The difference between the two is that the Young's modulus is basically what you measure when you're pulling the material apart and applying the strain, or the stress rather, in a pulling motion, whereas the storage modulus is when you're applying a compressive force. The loss modulus, on the other hand, is an expression of the energy lost due to frictional heating during loading and unloading of stress. So you determine that by taking the difference between the stress strain curve on the loading and the unloading portions of a measurement of a material. So when you're looking at the stiffness of the material, you've got as I mentioned before, the fundamental direct measurements of a DMA instrument is the force and the displacement. And the force will be ahead by some amount of time compared with the displacement. So you'll apply the force, and then the material will react and deform to the force. You can basically analyze the force and displacement curves to determine a number of different properties, such as the stiffness, which is basically the ratio of the force to the displacement at a given point during the cycle. You can also look at the modulus, either the loss modulus or the storage modulus, and a few other complex properties can be derived. You can also look at, for example, the modulus, the storage modulus or the loss modulus as a function of temperature. As I mentioned before, polymers have a very strong dependence of their mechanical properties on the temperature. And so you'll see a glass region, usually at very low temperatures, which will go through a glass transition range and enter a rubbery region where it's quite elastic. And eventually you'll get to a point where the rubber begins to melt, and that's when it'll start to behave less like a rubbery elastic material and more like a liquid material, in that it can flow. So that basically sums up the brief overview of our mechanical properties measurement methods. I would suggest Hugh Bourrier from Metroviv was so kind as to partner with us on a webinar a couple weeks ago, looking in more depth at thermomechanical DMA analysis of polymers. If Rosa can drop that link into the chat box, that would be very helpful. And I do recommend that if anybody has any interest in the DMA field and getting into more detail there, that you go check out that webinar. Our next topic is basically looking at how to characterize the thermal degradation of polymers. So I've got an image here of a overheated element on a circuit board, and you can see that the polymer casing on that has thermally degraded. So you can actually see toward the top of the image a little bit of soot marking on the on the board surface there, due to probably some smoke that was released by the polymer when it degraded. So it's important to realize when you're talking about thermal degradation in the context of polymers, there's not one single mechanism that can happen. Several different mechanisms can be at play, and in many cases, you might have several different mechanisms going on all at the same time. So it's important to understand a little bit about the chemistry of the polymer so you can determine what type of thermal degradation do you need to be worried about and what type of thermal degradation do you need to measure. So for example, you can have simple depolymerization, which is basically the reverse of the polymerization reaction that generated the polymer in the first place. In which case, the product of the depolymerization reaction is usually shorter chain polymers, or in some cases, simply simple monomers coming off of the chain. You can have side group elimination in the case of branch polymers. So that would be basically if you've got the longer chain and a branch shorter chain, the shorter chain might come off and result in giving you a short chain polymer and then the longer chain polymer. You can also have random chain scission, where basically the chain might randomly break at different locations. Finally, in oxidating atmospheres or on exposure to oxidizing materials, you can also have polymer oxidation occur. The most common form of polymer oxidation, of course, is burning. So examining the polymer's oxidation behavior is very important, especially for consumer goods that are going to go into somebody's household, because it directly pertains to the fire safety of that material. So how do we measure these different mechanisms of thermal degradation? Well, the short answer is there's two techniques that we would use. The first one being thermogravimetric analysis, and the second one being differential scanning calorimetry, or DSC. I'll first start with thermogravimetric analysis, or TGA. So for TGA, you're looking at the mass of the sample material and how that behaves as a function of time. So TGA is fundamentally a very simple technique, and it's good for looking at thermal stability and thermal degradation because in a kind of macroscopic sense. So how much of the polymer material is left after exposure to an oxidizing atmosphere at 400 degrees Celsius for a half hour? That's the kind of question that TGA as a technique can answer. So one of the most common applications of TGA is to look at thermal stability testing. So this is a really simple case study looking at polyethylene heated at 600 degrees Celsius, or heated up to 600 degrees Celsius at 10 degrees C per minute under an inert gas atmosphere. And you can see how the mass hits the decomposition temperature, and suddenly you have this massive drop off in the mass. And by looking at the DTG signal, you can see that there's at least two distinct steps in this process. And so that's kind of one of the examples of if you were wondering, well, what happens if my polyethylene material gets heated up to a very high temperature, this is the kind of experiment you would do to answer that question. Now, the other thing you can do with TGA, we won't be going into it in much detail in this webinar, but we might go into it in future webinars, is you can couple TGA with other techniques like FTIR or GCMS. And by so doing, you can observe what is being off-gassed by the polymer and correlate that to mass loss events going on your TGA curve. So that can let you take a look at, for example, what is the decomposition mechanism at play here. So that's another thing that can be done with these kinds of techniques. The other thing that you can take a look at is compositional studies. This is particularly useful, for example, in natural polymers like rubbers, as well as in natural analog materials like synthetic rubbers. So in this kind of a case, there's a variety of international standard test methods by ISO and ASTM, as well as a few other standards organizations out there. But generally speaking, what these look like is heating up first to an initial temperature at which you have an isotherm until things stop degrading to remove the lighter chain materials like plasticizers, oils, and waxes, and then heating up to a second temperature point to get off the heavier polymer chain materials such as elastomers. And then finally, you might burn it in air to determine how much carbon black and how much ash is present in the material. The other technique we had mentioned is differential scanning calorimetry. Generally speaking, under the primary technique used nowadays is the DSC technique, or differential scanning calorimetry, but there is a bit of an older technique called differential thermal analysis, and that's still used sometimes in some more challenging applications, where a cheaper, more easily replaceable sensor is sometimes attractive, or in cases where you really need to be super responsive to the onset of a thermal event, where the lower thermal mass of the DTA sensor can be useful in helping to resolve that. So some of the material properties that you're measuring when you're looking at DTA and DSC is you're looking at a heat flow as a function of temperature. So that can be useful in terms of examining things like thermal, the heat flow signal associated with thermal degradation. So for example, if you're looking at the oxidation induction time, as you can see on the right-hand side of this curve. So when you're measuring oxidation induction time, you'll heat up to a target temperature, in this case 210 degrees Celsius, under an inert gas flow, and then you kind of let the calorimeter equilibrate with the temperature point. Then what you'll do is change the gas flow over to oxygen or to air, depending on the experiment design, and observe how long the material takes to start being oxidized. And that's usually done with the simple two-line method. So you'll take the tangent of the straight line portion and the tangent of the steepest part after the oxidation has started. And where those two lines meet is determined as the oxidation induction time. There's other thermal events that can be observed by DSC. For example, you can look at the polymerization reaction itself. You can also look at things like polymer transitions. You can measure the specific heat capacity, and you can measure phase transitions. We also don't have time to go into it here, but with more advanced calorimetry equipment than we're highlighting today, you can also look at reaction calorimetry, where you'll mix, for example, you might look at what does the heat flow signal look like if I mix my monomer with my radical initiator and watch the polymerization reaction in an isothermal calorimeter. So that's something you can get into as well. Looking at highlighting the application to looking at polymers and phase transitions, you can take a look at this application data on polyethylene terephthalate. So we can see three different heat flow signals here. The first one on the leftmost side, that small one that you see, is the glass transition temperature. So in some cases, if there's a lot of thermal memory in the material, you'll see it as an endotherm there. Or in other cases, it might just look like a change in the slope, so a kink in the baseline of the heat flow signal. But in either case, it's pretty easy to resolve on a DSC signal. The second one is an exothermic crystallization of the amorphous phase of the polymer material, followed by the endothermic melting of the polymer. The next application we'll take a look at is looking at curing and cross-linking. So in this case, you might take a look at an uncured copolymer material. So for example, ethylene vinyl acetate. And you would heat it according to profiles similar to what you would use in the process, and measure the heat released by the curing reaction, and you can determine how much is already cured, or the degree of curing, by baseline, or by basically referencing your unknown sample to the behavior of a completely uncured material. A very common application for polymers DSC testing is looking at the specific heat capacity, because the specific heat capacity plays into so many different key important chemical engineering calculations. So for pan-style DSC, it's not the most accurate method of determining DSC, but you can get a very useful engineering number by pan-style DSC. And the way to do that is basically you run 3 different experiments and analyze them all together. The first one is just looking at the blank, which has your sample crucibles only, and that basically removes the effect of the calorimeter. The second one is the reference run, where you're comparing to, you're running basically a known standard to calibrate the heat flow signal of the calorimeter. Finally, you run your sample material, and the response of the instrument relative to the reference standard response is what lets you know what your heat capacity is of your sample. You can also, with a simultaneous thermal analysis instrument, you can study some types of TG and DSC or TG-DTA experiments simultaneously. So this is an example of a TG-DTA experiment where we're looking at free water content in a polymer. So on the top part there, you can see the mass loss signals due to loss of free water in the polymer material. On the bottom end of things, you can see the heat flow signals associated with the same phenomenon. So now that we've looked at the different heat flow signals that can be measured of different thermal events going on within a polymer, we'll take a look at the other side of things, which is more important in terms of designing the thermal management solutions, which is the heat transfer properties of the polymer material. So in a polymer material, the thermal conductivity is a function of the volumetric heat capacity, the speed of sound within the material, and the mean free path of phonons. So that's basically the case for most solids. And as the thermal conductivity increases, the mean free path of the phonon will decrease. So really, in this case, what that means is if you look at structures of different polymers and the effect of the structure on the mean free path, the more crystalline the polymer, the shorter that mean free path becomes. So we would expect, all else being equal, a more crystalline polymer would give you a higher thermal conductivity. And this is basically looking at a different way of describing the same, or a different property of polymers. So the other thing that will affect that mean free path is the degree of organization in the case of amorphous polymers. So if you have an amorphous polymer material, the degree of organization of the amorphous chains will also impact the heat transfer properties of the material. So if you have a situation like the one on the left where all the polymer chains are going all over the place, your mean free path is significantly longer. Whereas if they're all organized in a line, your mean free path becomes shorter and your thermal conductivity will increase. So this is one example looking at the effect of the crystallinity and the organization of a polymer on the thermal conductivity. We're looking at low density polyethylene, which is a branched polymer, versus high density polyethylene, which is linear and more organized. And you can see the high density polyethylene is almost half again more thermally conductive than the low density material. The reason for that is the linear high-density polyethylene is a lot more organized and therefore heat transfers a lot more efficiently within the molecules. So how do you actually measure the thermal conductivity? There's many different methods out there for measuring thermal conductivity. We'll be highlighting the three most common methods out there as far as transient methods go. So the first one is going to be the modified transient plane source method. This method is quite versatile. It's appropriate for solids, liquids, powders, and paste materials. The second one is the transient plane source method, or TPS method. That one is a very powerful method, a bit more difficult for the user to operate. So we recommend it for advanced users, but it does provide the highest level of control over your experimental parameters, and also unlocks some advanced data analysis capabilities that are not available on the MTPS method. The final method is the transient line source method, and that's most appropriate for soft materials, like, for example, polymer melt materials. So the first method that we'll look at application data for is the modified transient plane source method. And if you'd like some more details about how this method works, I encourage you to check out our method selection webinar that we did a few weeks back. Rosa's going to go ahead and drop the link to that one in the chat. We just have a lot of data to get through and not enough time to detail all the methods, but we do have a good resource available on our website free of charge. This method offers the greatest reproducibility of the three methods that we're highlighting today, and the best ease of use. You only need a single samples, and as I mentioned before, you can test solids, liquids, powders, and pastes with it. So this is some application data on silicone-based sealant material, which is a thermal set material. And as it cures, it will go from a tacky paste material into a flexible solid sample. So if you look at the thermal conductivity as a function of curing time, you can see for the different materials, one of them has significantly faster curing than the other. One is more thermally stable during its curing process, and the other has a significant increase in its thermal conductivity throughout the curing process, which really just goes to show the importance of being aware of how the thermal properties vary as a function of the curing time, and also being aware of what kind of curing process you're dealing with. Is the material a slow cure material or a faster cure material? So we always like to talk up our testing capabilities and our techniques, but what we say about our capabilities is not as important as what our clients say about it. And so this is an example of a testimonial from Stuart Sykes from Haydale Composite Solutions. He's working in the nano composites field. So Stuart Sykes says, the C-Therm TCI has been a key piece of testing equipment at Haydale, providing fast and accurate thermal conductivity measurements for our product development of nanocomposites. Having this capability has allowed a better understanding of the dispersion of nanomaterials in polymer matrices through thermal mapping sample surfaces. The support and customer service from C-Therm has been excellent over the years, and we look forward to dealing with them again in the near future. So some nice words from Stuart Sykes at Haydale there. The next method that we'll take a look at is the Flex Transient Plane Source method, or TPS method. This is a double-sided Kapton encapsulated sensor, which provides the greatest flexibility over the experimental parameters, including the test time and power parameters. It is recommended for more experienced users, so that you know how to, for example, set up valid test times and power parameters to get good quality data. But it has a few advantages. It doesn't require contact agents, and there's some specialty slab and anisotropy modules available. As well, it conforms to the ISO standard 22007-2. So oftentimes we get asked what anisotropy actually is and why it's important in the context of polymers. So anisotropy is basically a umbrella term for any kind of behavior where a material's properties differ as a function of which axis you're looking down for as far as the material's structure is concerned. So a common example of an anisotropic material would be something like wood, as you can see in the lower left-hand side. And if you're looking for measuring TPS, the TPS method in particular is valid for orthotropic samples. So if you look in the upper right-hand side, an orthotropic sample would be one where the thermal property, thermal conductivity, is the same in the X and Y dimensions, but different in the Z dimension. So there's a plane where the thermal conductivity is equal, more or less, and then the through plane direction, it's got a different thermal property. So when you're testing these samples, what you'll need to do is keep track of the in plane versus the through plane directions, and set up the experiment over the sensor in such a way that both samples are aligned in the same manner. So the in-plane directions are parallel, and the through-plane directions of each sample are parallel. And then you run a test in the software, and it will bring the data back. And if you have the volumetric heat capacity, you can deconvolute the in-plane thermal conductivity from the through-plane thermal conductivity. So as an example here, we're looking at a a nylon that has been modified with molybdenum disulfide, and you can see a photo of the sample on the right-hand side there. And so the nylon base material has a thermal conductivity of about 0.25 watt per meter Kelvin. And if you take a measurement of the composite material modified with the molybdenum disulfide, what we get is a thermal conductivity that is quite a bit higher, about 25% higher from the unmodified material. The final method that we'll look at is the transient line source. This method's best for kind of thick, goopy materials or unconsolidated solids. And it's standardized according to ASTM D5334 and D5970. So one of those is a method for looking at polymer melts and soft polymers. The other is a method for soft and unconsolidated geological materials. So what you can do in this case is take a look at the thermal conductivity of a polyamide 12 material as a function of temperature. And what we do is we will put the sample into a sample holder and insert the needle in, then melt the sample around the needle, and we just take the measurements and get this the thermal conductivity data. So again, speaking to what our clients say about our techniques, we've got a testimonial from Jose Fanesca from Covestro, which is a company working in the polymer sector. Jose says the C-Therm thermal conductivity analyzer has provided our group with a fast, accurate capability to test the thermal conductivity of our polymers with C-Therm's patented high-precision MPPS sensor. The instrument has become very popular within our group for its quick, easy, reliable measurement, and the support from C-Therm has exceeded our expectations. We recently upgraded the unit with the new robust TLS module for work on polymer melts. So that kind of sums up this very broad overview of the techniques for thermally characterizing polymer materials, ranging from thermal conductivity methods, DMA or dynamic mechanical analysis, as well as thermal analysis and calorimetry. At this point, we'll turn things over to Adam, and I'm sure he wants to speak a little bit about some of the upcoming webinars.
Yes, excellent. Thank you very much, Sarah. A great overview of polymers characterization. We do have a number of upcoming webinars in the month of July. So we're going to take a short break next week where we won't have any webinars, with it being a week to celebrate Canada Day here locally and 4th of July in the US. And so we're not going to schedule a webinar for next week, but the week after we've got characterizing battery thermal performance, and we'll look at the different aspects of characterizing battery performance from TGA, DSC, and thermal conductivity testing. The week after that, we're going to be looking at nanomaterials. And on the 23rd of July, we're going to be looking at textiles and validating performance claims around cool touch or warm feel, with a particular application towards bedding and other performance apparel in that space. So lots of great upcoming webinars. I see Rosa's already got that link in on the chat box. So please, we encourage you to consider registering. If you're not available at that time, but you would like to still receive a link to the recording, encourage you to fill out the registration form. You will automatically get a link to the recording once you've registered for the webinar. Even if you can't make the live event, you still receive that automatically. So encourage you to have a look. Okay. So I think we'll move on here. Sarah, if you want to advance to the next slide. We wanted to thank everyone. We know it's a busy time. I remarked in the webinar earlier this week that, we know that with COVID, a number of us are still working from home, some trying to balance parenting while working and still maintaining all of those responsibilities that the job demands. So, you taking an hour with us today really means a lot to us, and we really appreciate it. If you'd like to stay online with us, please do so. We are going to open it up for a Q&A session. But at this point, I want to thank Sarah for curating a great presentation on polymer characterization. I also want to thank Rosa Chen, who's been moderating today's session, done a great job. Rosa is our regional manager for China and Taiwan. Does a great job supporting clients locally in those regions, but also has jumped in here and been helping us out with moderating these sessions. So thank you very much for that, Rosa. And yeah, I think with that said, we'll transition to the Q&A session. If you're viewing this as a recording, we'll bid adieu and say thank you very much. And we'll stop the recording at this point. But wish you all a wonderful day, and hope to continue the discussion on a one-to-one basis. Okay, thanks everyone. Have a great day. Bye for now.